Hello friend, welcome to the course Quantitative UV Visible Spectroscopy. Many times the researcher or the student who is doing the practical in laboratory are facing the problem in quantitative UV visible spectroscopy in finding the concentration of unknown, preparation of calibration graph. So all this part will cover under this lecture. The content of my today's lecture is about the Beer-Lambert's law, method of analysis, that is single point calibration method, standard absorptive value method, calibration curve method, standard and sample preparation methods, spectrophotometer setup, care and handling, how to do the measurements, and data analysis. UV visible spectroscopy is widely used for quantitative analysis, particularly in determining the concentration of substance in solution. This is achieved by measuring the absorbance of a sample at specific wavelength and relating it to the concentration using Beer-Lambert's law. This law forms the foundations for quantitative UV visible analysis. It states that absorbance of solution is directly proportional to the concentration of analyte and the path length of the light beam passing through the solution. We will more focus on Beer's law. The intensity of transmitted beam of monochromatic light describes decreases exponentially with increase in concentration of absorbing substance arithmetically. In this diagram, you can see that P0 is the intensity of the incident light and P is the reduced intensity of the transmitted light. So whatever difference in these two intensity is the light which is absorbed by the substance present into the path length B. So this Beer-Lambert's law equations can more clearly be understood by using the Beer-Lambert's law equations. So IT equals to I0 to the base 10 minus epsilon CB is the result of the equation. The above equation can be written as log of I0 upon IT equals to epsilon BC, or we can write log of I0 upon IT as absorbance. Therefore, the equation becomes absorbance equals to epsilon BC or absorbance equals to small abc. So epsilon, where the epsilon is a molar absorptivity. If the concentration is expressed in grams moles per liter, we have to use the term molar absorptivity. If the concentration is expressed in grams per liter, we have to use the term absorptivity. C is a concentration. The unit of concentration is very important when we are finding the unknown concentration of sample. So what value we are using, whether we are using molar absorptivity value or where you are using the absorptivity values. B is the thickness of medium which remain constant, that is 1 centimeter path length. The amount of radiation absorbed may be measured in number of ways. Either we can measure in terms of the transmittance, that is T equals to I upon I0. Generally, this transmittance is measured in percent T. So we can write 100 multiplied by T, that is percent T. So absorbance can be written as A equals to log of I0 upon I, and in practice we are using these three equations. So A equals to log of 1 by T, absorbance equals to log of 100 by percent T, or log of 100 equals to 2. So we can write A equals to 2 minus log percent T. Generally we are using absorbance for all the quantitative estimations due to its linearity. Absorbance decreases as the concentration increases. So this linearity is maintained if you take the absorbance on the y-axis. The another quantity which can be used for calculation is the A11, which is indicating the absorbance of 1% solution in 1 centimeter path length. This is the standard absorbance value. So this can be used to calculate the concentration. So we have the equation A11 equals to observed absorbance divided by concentration into path length, where the path length is 1 centimeter, concentration is in percent, that is grams per 100 ml. So we will focus on the three methods which are used for quantitative estimation. The first one is a single standard or direct comparison method. A single point calibration in UV visible spectroscopy involves using a single standard solution to calibrate the instrument, assuming a linear relationship between absorbance and the concentration. This method is simpler than multi-point calibration, but may be less accurate if the assumption of linearity doesn't hold true over the entire measurement range. If your solution is obeying the BS law, maintaining the linearity, then and then only we can go for the single standard or direct comparison method. In quantitative estimation, we can calculate the concentration of unknown by using this equation C2 equals to A2 into C1 divided by A1, where C2 is a concentration of unknown, A2 is absorbance of unknown, C1 is a concentration of your standard, and A1 is absorbance of your standard. How this equation arrived? We know the Beer-Lambert Law equation A equals to ABC. Now, if we are having standard and sample, we can modify this equation. A1 equals to A1, B1, C1 and A2 equals to A2, B2, C2. So, we can write this equation as A1 upon A2 equals to A1, B1, C1 upon A2, B2, C2. Now we know that for the sample and standard, we are using the same cuvettes and the same procedures. So this absorptivity values and the path length remains constant. So they will get deleted from the equation. So the modified equation will be A1 upon A2 equals to C1 upon C2. If you do the cross multiplication and you simplify the equation, it will be C2 concentration of unknown equals to absorbance of your unknown multiplied by concentration of standard divided by absorbance of your standard. So just by doing this, we will get the answer of your unknown concentration. But you have to be very careful that what will be the unit of concentration you are getting. So as we are using this standard and sample, whatever unit of standard will be there, that will be the unit of concentration of your unknown also. If you are using microgram per ml concentration unit of standard, your sample concentration will also be in microgram per ml. So this is only possible if A11 is not available in literature, then we can go for these values. The second one is your standard absorptivity method, where the A1% 1 centimeter value is available, or the epsilon value or absorptivity values are available in the literature. The standard absorptivity method in UV visible spectroscopy utilizes known standard absorptivity values, also known as molar absorptivity or extension coefficient, or A1% 1 centimeter values, to determine the concentration of unknown substances. This method relies on the principle that the absorbance of substance at a specific wavelength, generally these A11 values or epsilon values are given at its lambda max, is directly proportional to its concentration and the path length of the light beam through the sample. Determining the standard absorptivity, that is epsilon, for a known substances. This standard absorptivity epsilon at a specific wavelength is usually provided in literature or can be experimentally determined. This value is characteristic property of the substance and the wavelength. So to find out the unknown concentration, we can use the Beer-Lambert Law equation, that A equals to epsilon Bc, and for finding the concentration C, we can modify the equation C equals to A upon B epsilon. So if you are using epsilon values, the concentration you will get will have the unit of gram moles per liter. If you are using the absorptivity value A, then the concentration unit will be grams per liter. And if you are having the A11 value, so we have the formula A11 equals to, A11 means absorbance of 1% solution in 1 centimeter path length equals to A upon BC. That is, to modify for the concentration, you will have the equation A upon A11. Now, the important thing, that what is the unit of concentration obtained by using the A11 value. So the unit of concentration will be grams per 100 ml. You have to remember these units to perform the further calculations. The third method which we are commonly utilizing is a calibration curve method or multiple standard method. We will more focus on this method while in this lecture. The calibration graph method in UV visible spectroscopy involves creating a graph, that is a calibration curve, that relates the absorbance of a solution to its known concentration. Means we are plotting the concentration of the known standard on x-axis and absorbance of the particular solution on y-axis. The concentration can be determined by using the line equation, that is y equals to mx plus c, where y is the absorbance of unknown solution, m is the slope of this line, and c is the intersect. You have to be very careful. C is not concentration. It is constant, that is intersect. And we can calculate the unknown concentration. So we will focus more on this calculation part in the next slides. The steps involved in calibration graph method, calibration curve method: preparation of standard solution. Prepare a series of solution with a known concentration of the substance you want to analyze. The concentration range should be chosen to cover the expected concentration range of your unknown sample. So whenever you are selecting the range, you have to be very careful that the absorbance should not be more than 1. If your absorbance you are getting is more than 1, that you need to dilute your solutions, even if it of standard or even if it is of your sample. Aim for at least 3 to 5 different concentration, with 5 being the ideal for more accurate curve. So whenever you are preparing a series of solution, at least use 5 standards, not less than 5 standard for the preparation of calibration curve. If you are using 3 or 4 standards, you will not get the accurate results. You have to be very careful that you are using more than 6 standards to prepare the calibration graph. The next step is measuring the absorbance. Use UV visible spectrophotometer to measure the absorbance of each standard solution at a specific wavelength. If I am saying specific wavelength, that is its lambda max. Lambda max is wavelength of maximum absorbance, the wavelength at which maximum absorbance of the solution is there. So to find out the lambda max, you do one thing, that you prepare a 10 microliter solution and you go into the spectrum mode, find the lambda max values from there, and rest of the quantitative estimations you can do it into the quantitative mode using the lambda max values which was shown in the spectrum mode. The wavelength is chosen based on where the substance absorbs the most light, the maximum absorbance wavelength, that is lambda max. Record the absorbance value for each standard solution. The third stage is creating the calibration curve. Plot the absorbance value on the y-axis and the corresponding concentration value on the x-axis. Draw a line, that is the best fit line, through the data points. Your all data point should lie on the line. If they are deviating, means you are having certain problems in preparing a standard curve. If the data point from a linear relationship, you can fit the linear regression equations. So this equation only useful if all points are lying onto the straight line. Okay, so we have the linear regression equation that y equals to mx plus c. Many times c is getting confused. So here I am written b. That is your intersect. The first step is determine the unknown concentration. How to find out the unknown concentration if you have the calibration graph. So here many people get stuck. Measuring the absorbance of your unknown sample at the same wavelength, use the standard. Okay, standard, whatever standard you are use, whatever wavelength of standard is there, use the same wavelength to measure the unknown concentration sample absorbance. Locate the absorbance value on x-axis of the calibration curve. Draw a line horizontally from the point to intersect with the calibration curve, the point where it will intersect on the x-axis. Drop a vertical line from the intersection point to the x-axis to find out the corresponding concentration. Alternatively, you can use the linear regression equation y equals to mx plus c to derive from the calibration curve to calculate the concentration of unknown sample based on absorbance. So whenever you are using this y equals to mx plus c, the unit of concentration will be the unit of your standard, because whatever standards we are using, a series of standard, if the standards are in ppm, that is microgram per ml, your sample will also in ppm or microgram per ml, concentration of your sample. Important points in calibration curve method, that the linearity. The calibration curve should be linear over the concentration range of interest. Many times we are observing R square value in the calibration graph. What is this R square value? That is a coefficient of determination indicating how well the data point fits the regression line. A value close to 1 suggests a good fit. If the value is 0.999, it is to be considered as good for the regression analysis. Limit of linearity. Many times, as the Beer-Lambert law we have studied, it has a certain limitations. The point where the calibration curve deviates from linearity, indicating the instrument is nearing saturation. If you are using very high concentration, you may get this limit of linearity. So you have to be very careful in selecting the concentration of your standard and sample. If you have done all the preparations of solution, now handling and care of spectrophotometer, you should focus. To properly handle and care for spectrophotometer, ensure it is kept in clean, regularly calibrated and operated with proper instruction. You have to follow the SOP, that is standard operating procedure. Read the standard operating procedure before you start using the instrument. Cleanliness, wipe down the exterior of the instrument with a soft, slightly damp cloth regularly. Before you start using and after use also, you clean the instrument from external surfaces also. Then you proceed for your further things. Clean the sample compartment thoroughly to remove the dust and debris. Do not spill any chemicals or solution into the sample compartment. It will cause the corrosion. Clean cuvette with appropriate cleaning solution before use, especially the optical surface. I will focus on the cuvette in the next slides. Remove dried silica bags from compartment before starting the instrument. In many instruments, a silica bag is kept into the compartment. So you have to remember that you have to remove that bag from the compartment before the self calibration is done by the instrument. If the bag is in the path of light, that will make wrong calibration of instrument and you will not be able to use it correctly. Do not keep cuvette in compartment or keep the lid open while self calibration of instrument going on. So you don't have to keep any solvent cuvette or empty cuvette in path of light. It should be free from all cuvettes, and close the lid of instrument so that no stray light can enter in the compartment. You have to be very careful when it is doing the self calibration. So do not open the window and do not keep anything into the compartment of the cuvettes. Now we will talk about the spectrophotometer cuvettes. A spectrophotometer cuvette is a small transparent container used to hold the sample in a spectrophotometer, and its primary types are categorized based on material like quartz or glass and path length, with proper handling requiring careful cleaning, holding by top to avoid fingerprints on the light passing surfaces, and choosing the appropriate coverage based on wavelength range of analysis and the sample compatibility. There are three types of cuvettes generally we are using in the laboratory: quartz cuvettes, glass cuvettes, and plastic cuvettes. If you are working in UV visible range, UV range specifically, you have to use the quartz cuvettes. If you are working in visible range only, then you can go for the glass cuvettes. And many times in the visible range, where the sample may get sticked on the surface of cuvettes, may destroy the surfaces of cuvette, we can go for the plastic cuvettes, which are disposable one. We can throw out the cuvettes after a single use, but they are not precise. Handling of this cuvette is very important. Clean thoroughly. Always clean the cuvettes with appropriate solvent before use to remove the fingerprints and contaminants. Never use harsh chemical like strong acid or strong alkalis to clean such cuvettes. Hold on the top edges to avoid touching the optical surfaces where light passes through. Hold cell only across the opaque wall for lifting. You can see the cuvettes in this slide. They are having the two are the transparent and two are the opaque. And a Q is written here. You have to check that your cuvette is written a Q or G. G stand for glass and Q stand for quartz. So you have to check, you have to handle this cuvette from this opaque surface only. Don't pick up the cuvettes from the clean surface. Whenever you are placing the cuvette in the compartment, you have to see that this plane surface should be in the path of light. By facing the ground surface towards you, you can keep the plane surface in path of light. Wipe with soft tissue. Gently wipe the external surfaces with lint-free tissue to remove dust particles. Avoid scratches due to the use of rough tissue paper. Simple tissue paper is not useful. You have to see that you are using a soft tissue paper to clean out the surface of these cuvettes. Match orientations. Ensure the cuvette is placed in the spectrophotometer with correct orientation to maintain constant light path. Many times the students are keeping the cuvettes in the opposite direction and no light passes through this opaque surface, ground surface, and then they are getting the wrong results. So you have to keep the cuvettes in such a way that ground surface should be facing you and clear surface should be in the path of light. Choose correct material. Many students, when they are doing the determinations, they are saying that they are not getting a clear graph after 250 before the 250 nanometers. So that is due to the use of glass cuvette. So if you are using the UV range, then you have to use the quartz cuvettes only, where the Q is written. Okay, select a cuvette material that is compatible with the wavelength range and chemical properties of your sample. Quartz cuvette should be used for UV range and glass cuvettes for the visible range. Chemical compatibility. Ensure the cuvette material does not react with your sample compartment like plastic. Teflon lids will be used only when handling the volatile samples. Okay, you can see these Teflon lids are there. Many students keeps the lids on the aqueous solution also. It is not necessary. The lid is only to avoid the volatilization of your sample, because it will change the concentration. So when we are using the organic solvent, then and then only you have to use the lid. See here the quartz is written on the side. Now the next part is preparation of the volumetric solutions, whatever solutions we are using. Weigh accurately the required amount of the substance. Weighing is the first source of error in preparation of solution. How accurately we are weighing the sample will decide all your determinations. So there are two methods of weighing: direct weighing method and weight by difference method. In many procedures, it is written that take accurately about. So what is accurately about? That is using the weight by difference method. In weight by difference method, we keep the material in a weighing bottle with lid. Take the initial weight of the bottle, sample and lid, then remove some quantity about quantity and again take the weight. Whatever difference in the first weight and the second weight is the exact amount of the samples you have withdrawn. So in many standard procedure, this word is written accurately about, indicating that you have to use the weight by difference method. So weighing is very crucial step in preparation of solution. Dissolve the substance in solvent. Fill the volumetric flask about 2/3 full with the solution. So whenever we are using the volumetric flask, use the volumetric flask with lid. And this volumetric flask is having one volume marking. Many students do one thing, that if the 1 ml is to be diluted to 10 ml, they are taking 1 ml and they are adding 9 ml with the pipette. So that is the wrong procedure. You have to use the volumetric pipettes or volumetric apparatus only, volumetric flask only to prepare the solution. Mix the solution thoroughly. Carefully fill the flask to mark on the neck. So whenever we are adding the solvent, it may make mistake in dilution, so that your layer or your solvent will be above this line. Excess addition of the solvent, it will destroy your solution. So be careful about this. When diluting the certain volume of solution with solvent, make sure to check the content before adjusting the final volume. In dilution methods, we are taking the 1 ml of stock solution and diluting with 10 ml up to the 10 ml, not with 10 ml. It is up to the 10 ml with the solvent. So in that cases, if you do not check the solution, there may be the various layers of the concentration, and every layer you will get the different reading. So be careful that once you are added the solvent, you have to shake it thoroughly before you adjust the final volume, so that it will mix. Otherwise, many student uses the ultrasonic water bath to mix the solution thoroughly. We are also facing how to prepare the ppm solutions, a series of ppm solution. What is ppm? That is 1 milligram per liter or 1 microgram per ml solution is known as a 1 ppm. Means if you want to make a 10 ppm solution, add 10 milligrams of the solute to 1 liter, that is 1000 milliliters of the solvent, or use dilution method as above. So mostly we are using the dilution methods in the laboratory, because we cannot prepare every solution 1 liter. So dilution method, how it is to be prepared: weigh 25 milligrams of the sample and dilute to the 25 ml. So that will prepare a 1000 ppm solution, that is known as the stock solution 1. Okay, so why I am saying 25 milligram? So if you are taking 10 milligram and diluting to the 10 ml, quantum of error will be more. Chances of quantum of error will be more, because exactly weighing 10 milligram is not possible. How much minimum quantity you are weighing, that much errors will be incorporated and that will be multiplied in every determination. So if you are preparing the stock solution, prepare with maximum quantity so that it will avoid the errors of weighing. From stock solution 1, take 1 ml and dilute to 10 ml. So 1000 divided by 10, that will be 100 ppm solution. Similarly, from stock solution 2, take 1 ml and dilute to 10 ml, that is 100 divided by 10, that is 10 ppm solution. Now we have the third stock solution, that is 10 ppm. From that, if you take 1 ml and dilute to 10 ml, 10 divided by 10, that is 1 ppm solution. Similarly, if you take 2, 4, 6 and 8 ml of stock solution 3 and dilute to 10 ml, the resultant solution will be 2, 4, 6 and 8 ppm. Now, whenever we are preparing such solution, see that the highest concentrated solution should not show absorbance more than 1. Means if you are using the 10 ppm solution as a highest concentrated solution, the absorbance should not be more than 1. If the absorbance is more than 1, you have to go in the further dilution process. Instead of using 1, 2, 4, 6, 8, 10 ppm, you can use 0.1, 0.2, 0.4, 0.6, 0.8 ppm. And if the absorbance is very small, then you can increase the concentration. That is, instead of using 2, 4, 6, 8, you can use 5, 10, 15, 20, 25 ppm solution, or 10, 20, 30, 40 ppm solution. That depends upon your sample concentration. So I hope that you have understood the dilution methods for preparation of a series of solutions. So this will help you to understand the quantitative estimations of the substance using UV visible spectroscopy. Thank you and happy learning. See you.